When I think of radio astronomy, the 1997 movie Contact usually comes to mind. In particular, the scenes of Ellie listening to signals on the Very Large Array radio telescopes. But what is radio astronomy really? I reached out to a radio astronomer to find out. I actually got into amateur radio in the hopes of learning more about radio astronomy. I did learn more about how radio signals work, but after speaking with Dr. Laura Driessen of the University of Sydney, I learned that it wasn't quite the same thing as what radio astronomers do.
So I think one of the problems with movies that use radio light is that they often are listening to the sound, right? And I think that kind of falls back onto kind of this weird misconception about radio that it is sound, because we think radio, right? And you think the radio, like you're listening to the radio. And that's a little bit of a problem for us radio astronomers, because people always say, oh, you're listening to space. And I'm like, no, you can only look at space. That's really looking at space or gravitational waves. Those are your only options for space.
So I can't hear them scream in space.
No, absolutely not. So I do love Contact. Don't worry. And she was totally listening to the right thing, but I think it just kind of falls back on that idea that radio is sound, which it isn't. So radio astronomy is astronomy where we collect light from the universe, but not the kind of light that we can see with our eyes. It's radio light instead. So it's the kind of light that's very, very long wavelength. I consider it like the base of light, because it's a long wavelength, really kind of like the low sounds that you hear, but light instead.
So it's not necessarily about sound wavelength, but light wavelength.
Yes,
and you're using these telescopes to get the wavelength itself.
Yes, so it's a little bit different to the way that we do. I mean, most cameras sort of work the same as your phone camera, where you consider light as almost like little tiny bullets kind of hitting a grid, and you almost count the number of bullets in one spot, and that's like the brightness. But radio, we're actually measuring light as a wave instead, and we measure it as it affects sort of electric fields instead. So it is a totally different way of thinking about astronomy and thinking about light. But yes, we are measuring light, and we're particularly measuring waves of light.
Basically, radio waves are just another type of wave on the electromagnetic spectrum. Unlike visible light, radio waves have much longer wavelengths and lower frequencies. Visible light wavelengths range from about 400 to 700 nanometers, which is incredibly tiny. In contrast, radio waves have much longer wavelengths, ranging from about 1 millimeter to several kilometers. These long wavelengths allow radio waves to pass through dust clouds and other obstacles in space that would block visible light. This makes radio waves very useful for astronomers who use special telescopes to capture and study them. Different wavelengths provide unique insights into various astronomical phenomena.
I think the trick here is that when we think about light, we think about the light that we see in our everyday life, and it's usually associated with heat. So fire we see it as light because it's hot. And that's almost the same with stars, right? Is that they have all this energy going on. Hot probably isn't, I mean, they are hot, but it's not sort of the right word. We call it thermal, where it's sort of light generated by heat. And that's how we think of light. But there's actually a whole bunch of other ways that you can make light. And that's what we're really probing when we do radio astronomy. And the main area, not totally exclusive, but the main area that radio light is made is in magnetic fields instead. So with radio light, we're really seeing the effects of magnetic fields on typically electrons. So that means that we can see the galactic center, which you can't see at any other wavelength really, because of all the stuff in between us and the galactic center. For stars, which is what I work on, we can see the stars that are particularly strong magnetically. We can see distant galaxies. The main thing when I take an image with one of our radio telescopes that we see is all these dots, just like when you look up at the night sky, except in the night sky, it's all stars. In a radio image, it's all black holes at the center of distant galaxies. So it's a whole range of things that you can't really see with your eyes, don't really have a good chance with your eyes at all, but mostly magnetic fields is sort of what we're seeing. Supernova remnants, supernova explosions, a whole lot of fun things in the radio that we wouldn't see otherwise. So I'm a postdoctoral research fellow, which basically means I've got my PhD and now have a job. So my first job was at the CSIRO, and this is my second job at the University of Sydney. And what I work on is radio stars in particular. So we think of stars, look up the night sky, we can see about 4,000 at once at a nice dark sky site if we have good vision, which obviously I'm excluded because of my glasses. I don't have good vision. So other people can see 4,000 stars. I can't. But when we look up at the night sky or the daytime sky, because it's a radio telescope, we actually only know about 1,000 radio stars. So these are stars that emit radio light. And this is interesting for a few reasons. So our sun is technically a radio star, but that's only because it's super close. If we put it at any kind of distance, it's weak, like in the radio. So, which is good, because if we see radio light from a star, that means that it's really what we call active. So lots of big chunks of plasma coming out, big X-ray flares, which I think is kind of fun, but is not so fun if you're living next to the star. So it's actually good that our sun is a very weak star. But the stars that I'm looking at, the fact that we can even see them with our telescopes means that they're kind of orders of magnitude, like hundreds of times more active and more magnetic than our sun. And we first learned about these stars in the 1960s before we even found about something called pulsars, which is one of the key areas that radio is really good at. But we still only know about 1,000 of them. So what I do at the moment is really searching for more of them using a telescope called ASKAP. And we're sort of entering a new revival, I suppose, is what you could say, in radio stars, because our telescopes for like 50 years, our telescopes just weren't kind of right for finding these things. And now we've got these telescopes that can see huge chunks of sky at once. They're doing big surveys multiple times of the whole sky. So we now have a chance to kind of get back into stars, and we're really learning a lot about them and about planets that might be orbiting them as well. So I think for me, I really love kind of digging through data and finding really interesting things. And radio astronomy has no shortage of data. That's one of the things we've never had a problem with. We've got heaps and heaps of data all the time. And in particular, ASKAP, the telescope that I use, the data are publicly available as soon as the team responsible for that data verifies it. So usually within a matter of weeks for our team, which is called VAST, the data are available even days sometimes if we're really onto it. And anyone can access that data, even the public can access that data. So there's just so much data that we're actually kind of just going, please take it. There's so much, we need people to look at it. But I absolutely love just getting a whole bunch of data, really digging through it, thinking of the physics that we're looking for and sort of those markers that we're looking for. And we do, in the team that I'm in, we do often find things that are just weird because we are kind of looking through everything and just going, what's in there? What weirdos can we find? So we do find a lot of interesting stuff that way. And I think that's sort of my favorite part of radio astronomy.
So speaking about weirdos in data, your opinion on the wow signal?
Oh,
yes, I'm hitting the golden oldies here.
No, I love it. I love it. So I think we have a bit of a different perspective on it now because we do find a lot of things that are really interesting. So the wow signal is most certainly interesting, but I'm in a team, I'm actually project scientist of a team called the Variable and Slow Transient Survey with ASKAP. So we're specifically looking for things that go boom, they flash, they get brighter and fainter. And we do often find things that happen once and then that's it. And we don't know what it could be and there's nothing there. So we often in radio, we'll find something, it'll flash, and then we'll look in observations that have been done in the optical and go, is there anything there? And then we'll look at x-rays and go, is there anything there? And often we'll see something, it'll go flash, and there's nothing there. And if we don't see it again, then there's sort of nothing that we can do about it. We just go, oh yeah, well, I guess there's something there, but we don't know what it is. So I think the wow signal is really, really interesting, 100%. But we do see things relatively often that we're just like, well, we don't know what that is. And I guess we might never, ever find out. So that actually does happen quite a bit. Do I think it's aliens? Unlikely. I think a lot of the things that we need to see, if we were going to confirm aliens, it's going to have a lot more going for it, really. A few of the things in radio, we always have a few frequencies that we're looking at. So we're usually looking at a range of frequencies rather than just one frequency. And we kind of think that if it's alien communication or something like that, it wouldn't be what we call broadband. We wouldn't detect it at a whole range of frequencies. It would just be quite narrow, mainly because of the energy that it takes to create a signal that goes across bandwidth. And also, as far as communications, we don't use a mobile signal that's insanely wide because that sort of is a waste of energy for us, right? We use really as narrow as we can because it just makes sense from an efficiency perspective. So I don't really think it's aliens, but I do think it's interesting because we do see these things that we just go, what the heck is it? And then we never see it again. And we always keep an eye out, but so maybe we'll see it again one day and then we'll be able to work out what it is.
Like Dr. Driessen said, radio astronomy isn't easy, but there are people out there who do amateur radio astronomy. If it's something you want to try, check out the Society of Amateur Radio Astronomers. Sarah is dedicated to the exploration of radio astronomy at the amateur level. Many amateurs are engaged in developing hardware, software, and methodologies to expand the limits of amateur radio observation. If you want to try building your own radio telescope, Physics Pier has a great tutorial, one I'll be trying this summer. Check the description below for a link to his video. Not up for building anything? That's okay. Dr. Driessen's got some advice for you.
So if you're out there with a telescope, I think one of the best things that you can do is look at galaxies. For example, Centaurus A, yes, that's right, Centaurus A is both a beautiful optical galaxy and an absolutely stunning radio galaxy. So I think there's a lot of things that you can look at with your telescope. Supernova remnants, for example, like Cassiopeia A, they're beautiful, and then in the radio they're also beautiful. So there's actually a lot of things where you could be looking stargazing with your eyes, maybe take some beautiful astrophotography, and then go and have a look at what it looks like in the radio, because things can look quite different, but it all complements each other. So I think the way that we think about radio astronomy is that we, as astronomers, we very rarely look in one frequency because that will never give us the full picture of what's going on. So radio really contributes to that. I think one of the main missions that I have as a stellar radio astronomer is actually making radio astronomy more accessible even to other astronomers, because most other astronomers wouldn't touch radio astronomy because it is really hard, especially since historically the data that you get is not nice. So we think take a photo with your phone, or even with a lot of the telescopes, it's almost immediately recognizable as a picture of space, right? Even with, you have to do corrections and adjustments, but you probably have some stars in there. You know, it's relatively kind of conceptually straightforward. But radio, we take the data and it's just a whole bunch of numbers and it's not even close to an image, and it takes hours from when you've taken the data to turning it into something that you can actually use as a scientific image or something like that. So radio astronomy has been relatively inaccessible until now, when telescopes are making process data. So the data that you can get from ASKAP is already an image. So all you need to do is download the image and you're good to go. So it is a trickier type of astronomy, but there's definitely resources out there. And if you're looking at some of these really beautiful objects in the sky, there's almost certainly a really nice radio image to accompany it. So I think if you're out there looking at space, it's not a bad idea to then come back in and have a look at what's going on in the radio with that thing that you're looking at, because quite a few things have some really interesting radio light coming from them.
Radio astronomy is a fascinating field that allows us to explore the universe by looking at radio waves, not listening to them. And while it can be complex, there are still ways for enthusiasts and beginners to get involved and give it a try. Whether it's through an organization like Sarah, local astronomy clubs, or YouTube videos like this. The opportunities to explore the universe through radio waves are within reach. Keep your curiosity alive, and remember, the sky is no longer the limit. It's just the beginning.
Thanks for watching. If you like this video, smash that like button. Click that subscribe button for more content from Texas Dark Skies, and ding that notification bell to get notifications when new videos are posted. Take care of yourselves, and in the words of my favorite personal astrophysicist, keep looking up.